welcome back after this small break, continuing what is basically now our security track. And Adrian has a very long career, first in HPC, working with processes, and then over 9 years at Red Hat. And he's going to talk about something very deep down. How do we do container forensics? Because as we heard from Rory, like if the logs are gone, they're gone. For a long time, this was a huge problem. And I'm really looking forward to this talk. So please, let's have it for Adrian Reber, Senior Principal Software Engineer at Red Hat.
Thank you for the introduction. Yeah, so I'm working on process migration, checkpoint restore, which is the basis for the forensic container checkpointing. What I'm talking about today for it's now, I think it's almost 14 years. I'm involved there. Then the tool we're using on the lowest level is called CREU, checkpoint restore in user space. I'm involved there upstream since 2012 at least, and since 2019 I'm mainly focusing on container migration. Starting from the lowest level, run C, run, and then taking it up the stack up to Kubernetes. Today's session will look something like this. I will give background about checkpoint restore. Maybe somebody hasn't heard about how it works and where it is used. Then I will talk about use cases, which might be interesting for container migration, container checkpoint restore outside of the forensic use case. Then I will talk about a forensic container analysis. This will mainly be a demo where I create a checkpoint and then go with you how I can analyze the checkpoint and see what was happening in the container when I took the checkpoint, and then a bit about the future, especially of checkpoint restore in context of Kubernetes. So checkpoint restore is done by a tool called CREU, which is called checkpoint restore in user space, and the reason why it's called in user space is because there were different implementation over the years which were implemented differently. So checkpoint restore is a technology which exists in operating systems for quite a long time now. And I think in Linux, it's at least 20 years that people have been using it. And one of the first uses of checkpointing and restoring processes has been definitely high performance computing. And there was an implementation called Berkeley Lab checkpoint restore, and there's also DMTCP, which is focused on high performance computing, but both solutions didn't find many users outside of high performance computing. And the reason was Berkeley Lab checkpoint restore was based on an external kernel module, which was never upstream, and for DMTCP you had to preload libraries to intercept system calls. So it was never what you would have called transparent checkpoint and restoring. So you had to prepare your operating system, you had to prepare your processes by preloading libraries. So it's not something you can just decide after the process is running, I want to checkpoint this process and restore it somewhere else, sometimes else. So that's why around 2007-08 there was a project going on also from high performance computing to implement checkpoint restore in the Linux kernel. It was a huge patch set. It was about 100 patches touching every Linux kernel subsystem, and it was working, but it was not accepted upstream because the community felt it was too complicated. So out of this approach, which was called checkpoint restore in kernel space, because it was implemented in the kernel, came checkpoint restore in user space, CREU, and that's why we have the name today. And CREU basically, from the beginning, it worked like it decided to use existing kernel interfaces as much as possible and try to work with what the kernel gives us and then implement checkpoint restore using that. And over the years, the CREU developers have added additional interfaces to the kernel. The interesting thing is most of these interfaces are never really 100% about checkpoint restore. They're always about how to figure out additional details from the process which is currently running. So it's always, checkpoint restore is always about getting information from the process that is running, storing it on disk, and then recreating the process as it was before. There are multiple integrations of CREU, especially in the container environment. And the first one to mention here is OpenVZ. It's a container runtime before the name container existed. I never used it myself, but a company behind OpenVZ was the group that they invented CREU. They developed CREU because OpenVZ was providing something like lightweight system containers, not like the OCI containers, which most people use today, where you have a single application running there. It was a complete system. You had SSH and everything in there in its system. And they wanted to be able to migrate those containers from one host to another, and that's why they created CREU. And the special thing here to remember is that CREU was developed for container migration and not like the other tools for high-performance computing. And this is also the reason why CREU today is used in many different container engines, container runtimes. An interesting use case of CREU, also something I have not seen myself. This is a Borg. This is Google's container engine. Google came to us maybe 2018, 17, something like this, and contributed some code, because from what we've been told from the Google people and also seen at conferences is that they use CREU container migration internally, and basically what they use it for is low priority containers which are running on a node. You have some high priority tasks running there, you need more resources, and instead of killing the container like before, losing the work you've done so far, they now just migrate the container to another host. The example they like to give is YouTube re-encoding, things like this, which run in the background, which are not time critical, but which you do not want to start from the beginning again. So there's also integration in LexC, LexD for a very long time. They've worked very close with the CREU developers from the beginning. There's integration in Docker for many years now. There's integration in Podman. This is something I've been working on since 2018, 17, I guess. And the goal was, from my side, if I can get working in Podman, then I can also maybe get it working in CRYO. This is Red Hat's CRI implementation, which is running under Kubernetes. And this work started in around 2020, and today it's merged. So today, and which things I will show you later, you can migrate a container using Kubernetes in combination with CRYO. Then recently I started to work on containerd support. The checkpointing part was merged, and it's currently part of the pre-release candidates from containerd 2.0. And currently only the checkpointing is available from containerd. The restore part, there's a pull request open for a couple of months now, but it hasn't been merged yet. So the story about Kubernetes and checkpoint restore, in the beginning we thought, how can we bring checkpoint restore to Kubernetes? And the problem is you have the CRI, and then without the CRI definition, you cannot implement it in the container runtime below. And without the implementation in the container runtime, you cannot implement it in Kubernetes. So we had to find a way how we can convince the Kubernetes community to take this feature into Kubernetes, especially in the kubelet. And so what we did, we came up with the story of forensic container checkpointing. This is something which especially banks are interested in. And the idea is you have your container running, and you think there might be an attack going on in your container, but you're not sure. You don't really want to stop it immediately because maybe then the attacker is gone or things like this. And so forensic container checkpointing gives you the possibility to create a stateful copy of all memory pages and of all changed files locally on disk. And this checkpoint can then be analyzed offline. You can restart a container in a sandbox environment where it doesn't have internet access. So and you can restart it as many times as you want, and the memory pages will of course not go away. So forensic container checkpointing is part of Kubernetes since it graduated to alpha level in 1.25 in 2022, and it became beta in 1.30 in 2025. And so today, with Kubernetes, you can create a checkpoint if you're using Cryo as the container engine, or if you use a pre-release of containerd, it's also possible. So use cases outside of forensic container checkpointing are, for example, the most easy or simple use case is reboot and save state. You basically have a container running in your host, and the container, you don't want to reboot your container because the service is you don't want to have too long downtimes or whatever. So what you can do with checkpoint restore is you can update the kernel, for example, then you create a copy of your container, write a container to disk, and then you reboot the host, and then with the new green kernel, you restore your container. And now, with checkpoint restore, you get a full stateful copy of your container. So all the memory is the same, everything is exactly the same as it was before. This is mainly useful if you have stateful containers. If you have stateless containers, then of course the whole migration thing and many use cases might not be useful. But the forensic analysis is also useful for stateless containers. The quick startup use case is also something which people actually use today in production. So you have a software as a service, for example. It takes 10 minutes to start, and you want to enable your customers to have the service ready in a couple of seconds. So what you can do is you take your container, you create a copy of the container, and then you can start multiple copies from the checkpoint. And the one we have seen, for example, was instead of 10 minutes startup times, you're down to a couple of seconds, because the startup time is basically just copying the memory pages from disk to memory, and then the thing is running again. And a combination of those use cases is maybe a live migration, so you have a container running on one host, you create a copy of the container, write it to disk, and then you can migrate it to another host, one copy, multiple copies, whatever fits your needs. Then spot instances is also something we see, or we upstream get contact about, is you take the cheap spot instances you can get from the cloud providers, and instead of losing all your work when the spot instance goes down, you take a checkpoint, write it to some centralized storage, and then restart your container, your application on a new spot instance. So this is also something people actually use today in production. And recently, a lot of people talk to us about GPU usage of containers, especially if you have your training running on a GPU, you want to do something else on your GPU, but you don't want to restart your training. This was a long time a topic where we upstream crew basically said, yeah, it's not possible because there's state in the GPU, or even if you talk about different devices, if you have an FPGA or an InfiniBand card, there's always state in your PCI device which you cannot get out if you just use the kernel. So you need additional support. But maybe a couple of years ago, AMD came to us and added support to Creo for checkpoint restoring GPU containers with AMD GPUs. So this works today. We can migrate a container using AMD GPUs in Podman from one host to another. This works. It also works in the context of Kubernetes. And just a couple of months ago, NVIDIA also released a tool. So today we are able to checkpoint containers with NVIDIA GPUs, AMD GPUs. And from what I can tell, NVIDIA is interested in making this more integrated in container engines and runtimes. Yeah, so those are the use cases. Now to my example, forensic container analysis. So what I will do now, I will start a really simple container in Kubernetes. So it's just a single container, a single pod, really simple. It's a stateful container, of course, so that it makes sense. So let's see. So it's running, and I can just talk to the container. It's just a web server, and it returns a number. It's stateful because it changes with each request. And additionally, I can write some data to the memory. So my random 1xx23 keys just in the memory of the container, and I can create files in the container just that we can later see that the files have been created. So what I can do now is I can create a checkpoint. Currently, checkpointing is a kubelet-only API, so it's not yet part of kubectl. I opened a pull request to make it part of kubectl, but currently I'm just talking to the kubelet, and this is just running on port 1025, and then there's a checkpoint API, and then there's a default namespace. Counters is the pod name, and counter is the name of the container. The checkpoint has been created. We created a tool to analyze checkpoints. It's called Checkpoint Control, and it just gives some overview. I'm just making the font smaller for a short time, so it basically tells us the name of the container, the base image, the ID, runtime, when it was created, the runtime, IPs. And the interesting thing is the checkpoint size. This is all the memory pages CREU dumped from memory to disk. And the rootfs diff size is the size of all the files that have changed in the container. So what I will do now is I will push, so the checkpoint archive is just a tar archive, and I will now put this into an OCI image and push this to a registry. I'm using Builder here to do this, so I'm copying the content to my new container. Then we defined an annotation so that the container engine later sees, okay, this is a checkpoint container. And then I think I have to do a commit. And then I'm deleting temporary container. And then I'm already pushing the container. Let's see, push. Yeah, so locally it's called checkpoint image latest, and I'm pushing it to the tag 62. So this VM is actually running 6 hours by train away from here, so it's a couple of 100 kilometers. And now I'm restoring the container on a VM locally here. So this is both VMs are Fedora 40, I think, yeah. And I'm running Kubernetes and CRYO from the latest Git checkout from today in the morning. So this is latest code, but it's there since 2022, I guess, yes. So my restore container definition looks something like this. So it's basically the same. I'm saying I want to create a pod, counters, and I create a container in it. I call it counter. And instead of specifying the original image, I'm now just specifying the checkpoint image. And now I say apply. And now I hope. Now I cannot see the screen. Okay, it looks like the container is running. You're in front of my screen. So, and now it shouldn't say 0, now it should say, I don't know, what was the last thing we did before? It should, 6, okay, let's see. And we have 7. So we did a stateful migration of a container from around 600 kilometers away to here, so this worked out. Another thing I want to do, and now I want to do the forensic analysis. I have shown the checkpoint control tool, which does a lot of this already. I'm creating another checkpoint. Now I do checkpoint control show CP. This is basically the same as before. And checkpoint control has one nice, another thing which is called, I think it's called inspect. And it gives me a tree. This is the same information as before as a tree, but I can also say all, and then it gives me much more information. And just let me go through it with you here. So what we additionally see is we see dump statistics. So we see the process was frozen for 59 milliseconds. We see how much CREU took to write the memory, how many memory pages were actually scanned, how many memory pages were written to the disk, and then we see the process tree here. So we have process ID 1, this is this one here, and it says this is the first process in the container. Then we see the environment variables, then another process in the container, and we see open files, for example, all the open files, all the variables, all the processes have. We see open sockets because it was a network process here. We see we have one process which is listening on the network. Then we see all the mounts of the container. And yeah, that's what checkpoint control can show you as an overview. Checkpoint control has also the possibility to take a look at the memory which was dumped. And previously I mentioned I've written some secret key to it, and it was called random1xx. And we see we can now find this information which was in the memory of the process now locally on disk. And this means we have access to every password, every random number, every private key. This is all visible in the checkpoint archive which was created. If the information from checkpoint control is not enough, then we can go a step deeper in the analysis. We can unpack the checkpoint, and we see here, this is the content of the checkpoint archive. So this is basically what we see here is basically metadata. We have information of the mount points. We have definition, or this is basically config.json, which runC uses. We have a copy here. We have the log file from Cryo. We have startstump. This was the information, how long it took to checkpoint the process. And we have the checkpoint directory. This is created by Cryo. And we have the rootfs div-tar. The rootfs div-tar file is all the changed files at the time of the checkpoint compared to the original image. And if I just unpack that one, we see there are just 3 files in here, and one is the log file. This is just a log file which is created, so you see all the everything which was written to the container file system, and the other files are just the ones I created with my create file interface. This is basically just to show how it looks if files are created in the container, how you can see them. The other information which is more interesting, or I don't know, which is also interesting, is these are the actual files which are created by Cryo during the checkpointing, and you can analyze it with CRIT. CRIT stands for Cryo Image Tool, and we can, for example, have a look at the UTS namespace information, and we see the container was using a UTS namespace, and UTS namespace is basically just the host name, and the host name of the pod was counters. We can also take a look at PS tree. PS tree will give us the information about the processes which we're running in. I can make this a bit simpler. So we see we have process 187 running inside of the container. Cryo always has the view from the inside of the container. If I look from the outside of the container, I see my process IDs are 20, 200, some big numbers here. So this is the view from the outside of from the host, but Cryo always has the information from inside of the host. What we can also do is we can list what kind of binary was running just by looking at this here, and then we see bash t counter, which is the same which we see here, which is currently running on the live system still. And so we can also use grep to grep for information through the pages images. The pages are basically just the raw memory data. This is the same thing checkpoint control did previously, where I was looking for my secret data there. So that's the thing about how you can analyze the checkpoint of the container, for example. I've shown checkpoint control, the tool which gives you a broad overview. I've shown CRIT, which gives you all the details about the data in your memory, about the process. Then grep you can use to go over the memory pages. So one other thing you can do is you can convert the checkpoint to a core dump, and then you can use GDB to analyze your processes. You can have a look at the registers and everything you want to do with GDB. And now to the last part. So what's next in the context of Kubernetes and checkpoint restore? Currently, we are mainly discussing still how to get kubectl checkpoint working or something in this direction. So I created a pull request, so an implementation exists, but I think we still need to figure out how to correctly provide it in Kubernetes in a sane way. I'm not sure that my first implementation is the best thing. Then what people always have been asking about is pod checkpoint restore, because currently what I've shown, I can checkpoint a container out of a pod and restore the container in another pod. And this even works if the first pod had multiple containers and the destination has only one container. So this all is possible at a point, but maybe people want to do a whole checkpoint restore of a complete pod. I've implemented this a couple of years ago, and it's not really hard because you just have to loop over the container, collect some metadata for the pod, and basically you're done. So this should be able to do if there's any if it's necessary. Then maybe in the far future, maybe something like kubectl migrate, where we can just say I want to migrate this container to another host without any of the steps I've currently done, which still requires a lot of manual commands. And then maybe a scheduler integration in, I don't know, 20 years. So that Kubernetes can decide, okay, resources are getting low, let's migrate this container somewhere else. What we're also doing upstream is we are trying to, the checkpoint OCI image I've shown you is just basically our idea how it could look like. We were trying to get a standard there, but this doesn't work really good, the discussion there, unfortunately. And with this, I'm at the end. So CREU can checkpoint and restore containers. It's integrated today in many different container runtimes. It's used in production by a lot of groups all around the world. There are multiple use cases, and the whole thing in Kubernetes can be found under the label Forensic Container Checkpointing, which is the CAP 2008. Thank you.
And an extra big applause for the first live demo, and what a hell of a demo that was.
Thank you.
I mean, I'm super impressed, mind blown. I was not aware that we were at this level of what is possible. And I guess there must be lots of questions, I would expect. Okay, yeah. Gentleman in the middle, please.
Yeah, this looks very scary. I mean, for security reasons, that you access stuff in memory right away. How can we not shoot our legs with this?
So,
Kurz wiederholen.
yeah. So the question was, this is very scary, accessing memory on the node, how can we not shoot our legs? Something like this, yeah. Yeah, so the important thing to remember is, if you root on your node, you can do all this today, so you don't need CREU, you can just use ptrace or whatever to analyze it. So it's nothing really new, it's just, we're putting it into a tarball, and then you can transfer the tarball anywhere, and then you have exposed your data more than root could do on your local machine. So, but the question you're asking is basically also why we take it so slow, why it's currently only a kubelet API and not kubectl, because we weren't aware of all the implications, and the plan was to make sure we don't introduce something which is really a big, scary problem, or I don't know. So, but I cannot really answer your question, so sorry. But it's a thing people think about, definitely, yes.
Yes?
I just wonder, you store all this information about IP addresses, mounts, etc. How can you restore this in the same cluster, in the P config, for example?
Again, please?
If you restore this on the same Kubernetes cluster,
Yes.
it also restores the IP addresses and everything?
So the question is, if we restore it, does it restore the IP addresses on the same cluster and everything? So this requires a bit of background. So CREU can checkpoint and so what I've shown you, it's just a listening socket. It's listening on 000. So this is not a problem at all. What CREU can also do is it can migrate established TCP connections. But this means on your destination system, you have to have the same IP address as on your host system. In Podman, we do this by if we see it's in restore, we just reuse the IP address, and this usually works. The thing is, currently what we do is we try to restore, and if it fails, then it fails, and then it doesn't work. But it doesn't break anything else, so just the restore will fail, and the rest of the system will just keep on running.
We have time for one more question. Yes, please.
Oh, it's always online. Yes, yeah. They reach out to us either on GitHub or sometimes it's a meeting and then we talk about it for a couple of meetings and things like this. Usually we get so people are interested in the technology and then they reach out to us upstream and try to figure out if their idea makes sense from our point of view or if it's wrong. So things like this is what we do. So the question was how do people reach out to us, if it's online or if it's a workshop?
If you're quick.
Okay, so does it recover host mounts? So yes, yeah, we basically, so in the end, all mounts, so we restore all bind mounts during restore, and if the directory or the file on the host doesn't exist, then the restore will fail. So all mount points or mount sources need to exist on the host system, and then the container will be restored, yes.
I think so too. That was extremely interesting, well delivered, and live. Applause for Adrian, and more questions later. Thank you
you.
so much. And speaker gift.
Thank you.